drugs, right? Right. So we're making drugs. If I'm working for a big company, I want to make them as many drugs as I possibly can because I need to make sure they're profiting. Everybody's all about the money, right? The more money. Okay, so you want to make sure that you have a high percent yield. High yield just means that you're making a lot for the chemicals or the reactants you're using. Just like on a farm. High yield means that all of your fields are producing maybe 99% vegetables, whatever you're trying to make, and you're losing very little. So if you think you should make 100 bushels of hay, you're making 100 bushels of hay. Or what would be a good yield? 95 bushels of hay? That would be great. 70 or lower ain't so good. You gotta try a different process, try a different method of making the stuff, the product you're making. So in my kitchen at home, so I've got this problem, like I want to make a dozen cookies, but somehow I end up with like 10 cookies. I don't know how it doesn't make a dozen. I make enough cookie dough for a dozen. I think my husband gets in there, or maybe me. I love cookie dough. It's a bad habit, but there's really not that much salmonella out there, so I'm safe. So I always want to make a certain amount. If you have higher amount of yield, you're an awesome chemist, okay? So theoretically, if I'm in the chemistry lab and I'm going to make 100 grams of Tylenol, theoretically I could, if I put enough reactants in there, I'm going to make 100 grams of Tylenol. But that's la la land. That's fantasy land. Nobody's that good. Walter White's like 97%, you know, but this is la la land. So that's an F. That's not an L. La la land. Okay, this does not happen too often. Make believe. It's a product that you think that you can make from the reactants you have to make the products that you want to make. But there's always some loss of chemicals. You don't scrape everything out of the way boat. Somebody sneezes on it, it goes everywhere. Whatever happens, happens. We're not perfect. So what we actually make in the lab, what we actually make is called the actual yield. That makes sense, right? So if I thought I could make 100 grams and I only make 95, I'm cool with that. I know I'm pretty darn close. So the closer your actual yield is to what you think you're going to get yield is, that means you're doing pretty good in the lab when you're making this. So this is what you can calculate on paper, and this is what you actually get in the lab. That's you have no choice. So when you're doing these kinds of percent yield problems, I'm not going to say, okay guys, let's go figure out what our actual yield is. And like go back there and do the lab real fast and see what we get. I'm going to have to tell you this in the question what the actual yield is. This you're going to calculate, and then we're going to compare. So a percent is what? A ratio, right? So my ratio for here, for us, is going to be what you actually get over what you thought you could get. That's what percent yield is. Do not mix this up with percent error. A lot of people mix this up with percent error. What's percent error?
Actual amount.
Actual amount minus experimental amount over actual times 100. That's percent error. This equation is different than actual yield over theoretical yield, which is percent yield. Okay? Don't mess, I know I'm trying not to mess with your brains too much, but they look kind of similar. And then as long as these are in the same units, you'll be okay in terms of calculating. There is no unit left on percent yield units though. So you'll have like mass, like actual mass over theoretical mass sometimes, so you'll be using grams, and then times 100 you'll get your percent yield. Alrighty? Let's do some problems with these then. Percent yield, what is the percent yield when 14 grams of magnesium chlorate, what would I call that? You or me? Okay. MgCl03. 2, okay. When magnesium chlorate decomposes and 3.0 liters of gas are collected at STP from decomposition. Okay, that's a lot of stuff. Let's figure out what's important. We need the 14 grams. That's going to be our known. What do you think this is? That's the product that somebody made in the lab, right? That's the actual yield. So they're actually telling you, okay, this person collected 3.00 liters of gas at STP from this decomposition. So what do you think that we need to do together find the theoretical, right? So we don't know the theoretical yield of oxygen gas. Oh, sorry, I just showed you the gas filter. Of the gas. How does this decompose? Does magnesium chloride decompose? What's the metal chloride? Which formula is? And O2, balance. Okay, so now we have 6 O's, 2 CLs, 1 magnesium. Awesome. Okay, so balance chemical equation, check. That's always your first step. 1, BCE. 2, start with your known and figure out what you have to do. 2-step process, right guys? Right. Okay, so I know that I'm starting with 14 grams of MgClO3, 2. What's the only thing I can do with grams? Right, convert to molar mass, or convert using molar mass. I have that for you, if I find it fast enough. That is 1 mole of magnesium chlorate weighs 100 or 190.9 grams of magnesium chlorate. All right, what do I want to get to? What identity? What chemical? Oxygen. That's because I'm told that I have an actual yield of 3.00 liters of gas, and the only gas created is oxygen gas. So that's what I have. My units have to be the same between actual yield and theoretical yield. So I need to know how many liters of O2 gas I'm creating. That's my question. So how do I get there when I'm stuck right now in moles of magnesium chlorate? What has to go on bottom? Moles. How do you know 1 mole? How do you know it? All right, but I don't know the number here yet. Where am I going to look to know that number? Balance chemical equation, that ratio. And yes, it is a 1, but I want to make sure we were looking at there and not looking at that. Huh? To 3, right. So 1 mole of magnesium chlorate to 3 moles of oxygen. And then last step. Right, because you can use that this time because we're dealing with what? A gas. 22.4 liters per 1 mole of O2. So when you multiply 14 divided by 190.9 times 3 divided by, times 22.4, that gives us 4.928 liters of O2. This was my what yield? Theoretical yield. This is la la land. Oh yeah, if she's real good, she can get about 5 liters of oxygen. But in real life, we only got 3 liters of oxygen. How do I get percent yield? Right, actual yield over theoretical yield times 100. So actual yield was 3 liters. Theoretical yield is 4.92 liters, or 93, I guess, to be around. Times 100, what is that? I heard somebody, thank you. 61-ish%. Is this person really good in the lab? I mean, like, maybe they're a rookie and they're still working at it, but come on, 61%? We can do better. We can do better. So I'm going to test your percent yield on Monday. We're going to make sodium chloride from hydrochloric acid and sodium hydroxide. We're going to make it, and it's actually going to look just like salt you shake out of the salt shaker. We're going to see who can get the best yield. Whoever gets the best yield gets extra credit. Okay? So that means I'm going to test your awesomeness in the lab. Okay, so not like a challenge, but you know, I like a little competition every now and then.
So you're leaving a grade up to nature.
Yes. Yes. I can go back 22. Do I need to? Sorry, stay right there for a second. Alright, I need okay, who's like really good at making peanut butter jellies?
Dude,
Okay, so Madison. Okay, so what's the best recipe for peanut butter jellies? If you're done writing, you write this down.
cool. You know,
What's gonna
jelly,
jelly?
jelly really nasty.
What?
Apple jelly. It's what they're blackberry.
Apple.
I need the recipe. Like, I need a sandwich base. Can I get a sandwich base? Alright, so I've got my bread. My bread, you know, white bread. Yeah, I'm gonna use your white bread.
Oh,
I got this blackberry jelly apparently. Okay. You like my peanut butter?
Oh yeah.
It's that the smooth peanut butter, not chunky, no chunky.
No chunky.
I mean, you don't.
No.
And it's starting to peanut butter reduced okay, my mom, so I really like peanut butter. My mom bought me at Sam's Club this big, like, 6-pound peanut butter jar for Christmas as a joke about 4 or 5 years ago now. The day after, got recalled. I was like, what am I going to do with this 6 pounds of peanut butter? What? I don't know.
If it's recalled, you take it back.
It was like $10.
It's $10.
Recall.
Salmonella.
Oh.
Okay. So,
Did you eat any of
Where did you take it back?
no, I did not. I threw it away.
I would have kept it.
Okay, so I need for my professional sandwich maker to come and see how fast you can make sandwiches. Come on, Reese, you're volunteering. Okay, so I want to see this. Oh no. No, professional sandwich makers have to be efficient. Bread, jelly, peanut butter. All right, sir, you're on the spot. 3, 2, 1, go. Okay, cheer on, people. Okay, bread, sandwich, peanut butter. 1. Bread, sandwich, peanut butter. Where's the top? Okay, cool. Let's say like open face peanut butter.
There's too many jellies.
What? What? Oh, some bread butter? Peanut butter? Half. What? What? What happened? What happened? I got a
Bread.
what?
Bread.
Bread?
In the first place?
So what was my? I know I set you up. Set you up. So what did we run out of?
Bread.
So what was my limiting reagent?
The bread.
So I didn't have enough reactants to make all the products? Oh my gosh, is that chemistry in action or what? Thank you, Jake, for letting us share house of the sandwich place. Yeah. Okay, so now I want to tell you about limiting reagents. Thank you, Madison, for your awesome sandwich making skills. And thank you. I like to do some crazy stuff.
These are real bread and jelly.
Oh yeah, no, I did not bring your own bread and jelly because then I would have eaten all the peanut butter. And they would have been fun jelly sandwiches. Oh no, I could have gone to the food spot. Okay. Yes, limiting reagent and limiting reactant mean exactly the same thing. Yes. So a reagent is just something that you use to make products. So limiting reactant means exactly the same thing. So in our example, we ran out of bread. So what's the job of a limiting reagent or reactant? It's going to limit what? The number of products. So what did we have in excess in that example?
Jellies
and yeah, we had excess jelly and peanut butter. In our examples, we're just going to have we're going to have 2 reactants total. One will be our LR or our limiting reagent, and one will be our excess. Get that? Get it? Excess. Yeah, okay. So one will be our leftovers that we got to put back in the fridge and save for later. So the limiting reagent will tell us how much product we can get, and the excess will just be leftover, and we can calculate the grams leftover, and when we get into these types of problems. I have 2 ways that I like to teach this. Actually, there's like 3. My teacher taught me one, made absolutely no sense at all, so I'm not teaching it that way. I found another way I like, and I'm going to see if you guys like it, and then because my AP chemistry students, they've had me for honors in AP, so I've taught them like 3 ways to do everything. And they were like, "This is the best way, so we stick it this way." So we can do this together, an easy way. So when you're doing limiting reagent problems, we have a process. We always do the same a similar approach. First thing you have to do is you have to figure out who is the limiting reagent. Because if the limiting reactant is controlling your products made, you have to know who it is so you can do the math with that. So how do you figure out who it is? You have to convert everything to moles, kind of like our general rule of thumb is convert everything to moles. And then you compare them using your mole ratios. So in our example, I think we had like, let's call it 10 pieces of bread. And then we had no, we had, okay, I'll say 15 pieces of jelly. Okay, it was a piece of jelly. So it's one of those nice, foot roll-up jellies, you know? Okay. So we have 10 pieces of bread. We have 15 pieces of jelly. In our case, we ran out of bread first, right? Well, what I've done here is this is my moles of bread and my moles of jelly. And my recipe was like 2 pieces of bread plus 1 jelly plus 1 peanut butter. 1 peanut butter makes 1 PB&J. PB&J. So my ratio between bread and jelly was a 2-to-1 ratio, right? I needed 2 pieces of bread and 1 piece of jelly to make a sandwich, you know? So in the example here, if I have 10 pieces of bread, how many pieces of jelly would I need to fulfill all that bread? 5, right? So what I'm doing in my head is I'm going, okay, for every 10 pieces of bread, my ratio used is 1 piece of jelly for every 2 pieces of bread. You just did that in your head, right? 10 divided by 2 is 5 pieces of jelly needed. Did I have 5 pieces of jelly? Yeah, I had way more than that. So my jelly's not running out. What was running out? Bread. So I can double check this. I have 15 pieces of jelly. What's my ratio? 2 pieces of bread per 1 jelly. And so I would have needed, 30 pieces of bread to complete my transaction of making sandwiches, right? Did I have 30 pieces of bread? No, I only had 10. So who's my limiting reagent? Bread. Okay, can you understand that example all the way? Pretty well? We're doing that with chemicals now, okay? Yeah. The rest of it's just sitting in the bowl. It's just sitting in that peanut butter jar or that whatever thing we have it in. It doesn't do anything. It just sits there and does absolutely nothing. Yeah.
So the jelly, would that be the excess?
That would be the excess.
We don't do anything with that?
No, we don't. We can calculate with it, but we're not going to do anything with it because it's going to be chilling there by itself until somebody goes to the store and gets some more bread.
Okay.
Okay. All right. So here's my first example. Hopper, write down your notes here. Okay, so reaction between iron and copper 2 nitrate, BC. First, what is it?
Fe plus C plus nitrate, and then 2
Yields.
salt.
It is iron 3. Good job. Balance. It's not balanced. Balance.
A 2 is for the second.
A 2 in front of over here. Over here. Where do you want to go?
The
You see, I have a 2 here for nitrate and a 3 here for nitrate. So what am I have to do?
3.
And
then a 2 in front of that. And then 2 in
I got you. So once I have those 2 here, 2 times 3 is 6 nitrates. Now I have 3 coppers I have to deal with, so I have to put the 3 here in front of the copper, and that 2 in front of the iron satisfied my 6 nitrates, but the 2 in front of the iron has to be balanced as well. Okay, so I think I'll start shooting like water guns in school, shooting people. Okay, so we have 3.6 grams of iron, and we are not only given one known, but we're given multiple knowns. So this is the problem. When you have problems where you're given information about, grams or moles about both reactants, that's when you know it's a limiting reagent problem. Because it says, I've got 2 reactants to deal with. Who is my LR? That's what it means when you're given information about both reactants. So I'm not always going to tell you when it's a limiting reagent problem. Okay, you're going to say, ooh, I'm given quantities about both. That means that's a limiting reagent problem. That's because you got to figure out who do I use for the calculations. So I need to first figure out who the LR is. So that's part A. So let's start with part A. All right, so this is how you start it. What was the first step? Back on the example. Right, convert to moles. So we have 3.60 grams of iron. How do I get to moles? Molar mass. 1 mole of iron. And thank you. 55.85 grams of iron. All right, I'm now to moles of iron, which is 0.064 4 or 5 moles of iron. And please, everybody do this exactly like this. Write this as a have. This is how much you have of iron. Because this is going to have a lot of numbers, and I want you to be able to locate what you have. Because that's what I have, and all I did was convert it to moles. I didn't change the darn thing. All right, second part is to convert the other one to moles. So how do I get moles when I have liters and molarity?
You convert the milliliters to liters.
Okay.
0.005.
Okay, sorry, I'll make a screw up here. 0.005 liters. Can you all do that in your head? Fine. Move the decimal back 3 spaces. And then what?
And then multiply by 5.
Right, so essentially I'm doing M times V to give me moles. M is here, V is here. Multiply them together to get moles. To multiply by 0.51 moles of copper 2 nitrate over 1 liter. Because don't forget that this molarity thing means moles per liter. That's our conversion factor. So 0.005 times 0.51 is 0.0026 moles of copper 2 nitrate. Alright, and then this is also a half. This is how much I have of copper 2 nitrate. So write half above that one as well. Alright, first step accomplished. We have moles of both reactants. Now what do I need to do? What did it say in your previous slide?
Compare reactants.
With what?
The ratio between pieces.
Right, using the ratio. So what's the ratio between iron and copper 2 nitrate?
Every 2 ions.
So we have 2 irons for every 3 coppers, right? So I'm going to compare by writing out this dimensional analysis, this conversion factor. For every 3 moles of copper 2 nitrate, sorry, this is kind of small, I'm using how many moles of iron? 2 moles of iron. The reason I do it this way is because I need moles of iron here to cancel with moles of iron here. Does that make sense?
So,
It's just like normal. You cancel top and bottom. So if I have 0.64 mole, 0.4645 moles of iron, and I have a 3 to 2 ratio, all I'm going to do is say that times 3 divided by 2. That requires, I'm going to write this answer up here, 0.09675 moles of copper 2 nitrate. And I kind of just said it, but that's called my need. If I have this much iron, how much do I need of copper 2 nitrate to fully react with all of it? Does that kind of make sense, like the bread and peanut or the jelly example? If I have this much iron, fully react with that, I need 3 copper 2 nitrates for every 2 irons. So I need to multiply this by 3 divided by 2. That tells me I need, they need up here, 0.09675 moles of copper 2 nitrate. I need that much, and I have that much. I have 0.026. I need 0.09. What's wrong? I don't have enough, right? So do I know who my limiting reagent is? Which one?
the other 2
The copper 2 nitrate, the one I'm pointing at right here. So if I have 0.026 moles of copper 2 nitrate, and I just found out I needed 0.9 of the copper 2 nitrate, I don't have enough copper 2 nitrate. I don't even have to figure out how much I needed the other one. I probably do for farther down the problem, but right now I know who my limiting reagent is. It's the one I don't have enough of, which is the copper 2 nitrate. Okay? So this is my LR. LR is copper 2 nitrate, excess is iron. I like to label it above on the PCE because it makes me just a little bit organized, yeah.
The 2 times 0.064.
I was showing you the ratios. So I was saying if I have this much of the iron, it reacts in a 3 to 2 ratio. So I need 3 moles of copper 2 nitrate for every 2 moles of iron. So that's a 3 to 2 ratio. So I just have to say this times 3 over 2 to figure out how much I need of that reactant I have on top right here. And I'm going to show you this bottom one here too. So what's my mole ratio between iron and copper again? So 2 goes on top. So 2 moles of iron on top, and on the bottom I need 3 moles of copper 2 nitrate. So this copper 2 nitrate cancels with this copper 2 nitrate down here, And that leaves me with having 0.0026 times 2 over 3, which was 0.001733 moles of iron that I have or need. Okay, so if I need 0.0017 iron, how much do I have of iron? Plenty. I've got 0.06, right? I only need 0.001. I'm good. I've got plenty of iron, so I've got excess of iron. Does that make sense? Keep working with me here, okay? Because this is the hard part. That's like, we are over the hill. We are good. We know who the LR is. The whole reason we did that is because we need to know who to proceed through the rest of the problem with. Now we know it's copper 2 nitrate. Yeah.
So how did you get how much you needed of iron?
I found the mole ratio between copper 2 nitrate and iron, and I put it like I would normally want to for canceling units. So I just put 2 over 3 because I have a 2 to 3 ratio here. So that's why you have to do species. All right, next part. How much copper will precipitate out from the reaction? So that's the question B is pretty much saying how many grams of copper do I create? That's my question. My starting point now, I'll go ahead and put a star by this. Your starting point now is your half of your LR. That's the whole reason you did all this mess, is to find what your LR is. So how much do I have of my LR, my limiting reagent? 0.026, because copper 2 nitrate was my LR. So I'm going to start with my half of my LR, 0.026. I just like this big, so I'm just going to keep it like this. So question mark, how many grams of copper can I make from 0.0026 moles of copper 2 nitrate? Alright, you know how to get from moles to anything else. So if I have moles of copper 2 nitrate, what do you want me to do? I want to get to just plain old copper, right? What's your BC? Yeah. What's my ratio? 3 to 3. So the question was how many grams of copper comes from my LR? Right, this is a 3 to 3. If you got to point it on your paper, point at it until you can start to see it. So this is a 3 to 3 ratio. So if I'm starting with 0.026 moles of copper 2 nitrate, I need to go to just general copper, plain old copper. 3 moles of copper are formed on the product side for every 3 moles of copper 2 nitrate used. Okay? And then now I want 82 grams of that. So what's your next step? Molar mass, right. So 1 mole of copper is 63.55 grams of copper. And that gives me 0.165 grams of copper. This is general stuff. You were doing this yesterday. The hard part was to try to figure out who your LR is, who your limiting reagent is. So now you go moles to grams. That's your answer. All right, the last one is probably the last one I'll do, and I'll let you guys start yours. I really like you to do like 1 or 2 examples of these things, and then you can roll with it. C said, how much of the excess reactant is left over? So you just subtract, and that's it. So, but what you need to do is find who's your excess in this problem? Iron. The way you do it is you take what you have. Oops, that's going to be half of your excess minus your needed amount of the excess reactant to figure out how much you have left over of your excess reactant. Because if you have a lot and you only use a little bit, you're going to have leftover, right? So how much do I have of my iron in moles? 0.0 what? 645 moles of iron. How much do I need of that?
0.0017.
Right. See, if you label it, it's really helpful because when you're going back and looking for these numbers, wherever you see a big have, you look for that. Wherever you have a big need, you look for that. So minus 0.001733 moles that you needed. So 0.645 minus 0.001733 is 0.062767 moles. I'm extending that out because I just need to take this and I need to go to grams. Because when it says how much, that's what you guys yesterday, much meant what? grams, mass. So all we gotta do is convert this to mass. How? Molar mass. So that many moles, 1 mole of iron weighs 55.85, thank you, grams of iron. And that is 3.51 grams of iron. Alright, stand up. Stand up, stand up. That should stand up. Alright, forward lap. Okay, do you stand spacing because you just finished your first living arrangement problem? And this is the worst of chemistry.
I can't breathe in.
Okay, thank you for this. Let's do another one. Your first living reagent problem, guys. This is like big boy chemistry. But it does take like half a page of homework, I know. That is one problem. Alright, please start that one yourself. If you took good notes on the first one, you'd be awesome on the second one. Ask the person next to you. Sean, you okay? Can you stand up? Stand up at a lab station work. Because you didn't hear any, I don't think, of my first example. Do what? For chapter there? AG. I think that's point 4. We don't even have to do that section. Okay. Doesn't have to. Alright, spot check. What's your BCE?
C nitrate, AG plus copper nitrate.
Beautiful. Okay. Good. Alright, keep going. No, you could have balanced that. You just didn't get on it yet.
So for every 2 silvers, there's 1
Yeah.
Is this the
decimal back 3 spaces.
Is that what you got? Okay, is that what you got?
Yes.
Okay, what's that?
You know, I got
Yes. And that's silver. Yeah, you do half? No. We need half. So that's how, right? If we need more than we have, right?
Where's my little remote?
Okay. So now, how much silver? How much silver?
You do. To get
So, oh, the ratio of silver, so.
All right, so then you know who your LR is, you can proceed. What's the second question saying? How much silver solid can you make?
How much silver?
Okay. How much silver can you precipitate out or something like that? Okay. The whole reason you did this is so you know who your LR is, check, and so you know what to start with for the rest of it. What did I tell you to start with for the rest of it? Your what? Your half of your LR, right? What do you have? What do you have of your LR? Wait, what? Yes, it's the silver one, right? So that one. So now you're starting off with 0.040 moles of silver nitrate. You want to get to how many grams of silver you can make. First step, mole ratio, right? So this ratio is a 2 to 2, so between the silver nitrate and the silver. So 2 moles of silver are created for every 2 moles of silver nitrate used. Last step. Right. What's the mass? What's the molar mass? Thank you. Something like that. And that's going to create. I got 4.3. I think you just corrected. You probably have to divide by 2 versus times by 2 or over 2. But you got half of that. All right. This is theoretically how much you can make of silver, right? That's important because later on you're doing percent yield. So I'm going to go ahead and label this my theoretical yield because that's my TY, my theoretical yield. All right, part C asks for what? How much do you have left over in excess? All right, use your excess reagent. Copper. So how did you do this before? Have minus need gives you leftover. How much did you have of your copper? 0.0393 moles of copper. How much did you need of copper? 0.02 moles of copper. So much do you have left over? 0.0119. Yeah. All right. But much does not mean moles. It means mass, right? Grams. So last step.
Multiply by copper.
Right. 63.55 grams of copper over 1 mole of copper. That gives us like 1.23 grams of copper. Good job, guys. All right. So in my beaker, at the end of this reaction, what do I have? In my beaker, if this was happening in a beaker, what do I have? I've made copper nitrate, right? I know I've made copper 2 nitrate. I've also made silver. What else do I have? Why copper? because it's your excess. So what I would say is, which of the following is not left over at the end of a reaction? Which of the following is not left over at the end of a reaction? The silver nitrate, because it's your what? Eliminating reagent. Okay. All right. The last step was to find the percent yield. So it said in the problem this person made how much? I mean what? I can't make that. 3.64 grams of silver is what they actually made in the lab as your actual yield. What did you get as your theoretical? 4.3 grams of silver. Percent yield is what? 84. They're getting there. They're pretty good. That's good yield. 84 is pretty good. Yeah.
If our numbers vary slightly, like I got 1.12 instead of 1.23, is that?
I easily can make an error like in masses, so yeah, we should be closer than that actually, so I can double check my math, but it should be close. Yeah. Yeah. Alright, for those of you who are okay with this stuff, pull out problem set 12. Your homework tonight is to continue problem set 12 and bring in chocolate. You have 20 minutes right now. You can probably get 10, okay, let's say 5 problems done. Work on it. I can pull up problem set 12 right now as well. I see your hands, but this way. Start a problem for me first. We have 25 minutes in order to ask me questions now. If you can wait a couple minutes to get started.